Let's continue with some more problems. The next problem is, at what angle should a ray of light incident on the face of an equilateral prism so that it just suffers total internal reflection at the opposite face? The refractive index of the material of the prism is 1.5. Let's do this. So they have given that we have an equilateral prism. So for an equilateral prism, you know that the angle of the prism is equal to 60 degrees. This is the base of a prism, and when light is entering into a prism which is falling at one face with certain angle of incidence, say that the angle of incidence is equal to some I, and now the ray is passing through the prism, and at the opposite face it just suffers the total internal reflection, which means the ray is just passing along the interface like this. They are saying that the refracted ray from the other face is just traveling along the face. It is just suffering the total internal reflection. So when you draw a normal at this point, the normal is like this, means so this angle of emergence is equal to 90 degrees. Correct? See, this is angle of incidence, and at this point you can write this angle as angle of refraction R1, and this is the angle of refraction R2 for the second phase. If you observe the diagram, they are saying that at the opposite face it is just suffering the total internal reflection, which means the angle R2 should be equal to the critical angle. Correct? Only for critical angle the ray can pass along the interface. Means this angle R2 should be equal to IC, which is nothing but a critical angle. For the second refraction, the angle of refraction R2 will be equal to the critical angle. So what we need to find in this problem is, we need to find what is this angle of incidence. For which angle of incidence the emergent ray is passing along the interface, or it just suffers the total internal reflection. That we need to find. Let's do this problem. They have also given that the value of refractive index of the prism is 1.5, so that we have a relation for refractive index of the prism with a critical angle, which is given by 1 over sine IC. Correct? N is equal to 1 divided by sine IC. We have this formula. Now by using this formula, we need to find what is this IC. Then I will be knowing the value of this R2, correct? Because IC is equal to R2 for the second phase. Therefore, if I find the value of IC, then I can find the value of R2, correct? Therefore, let's do this. From this formula, if I rearrange this, we get sine IC is equal to 1 over n, or IC is equal to sine inverse of 1 by n, where n is the refractive index of the prism. So the refractive index of the prism is given as 1.5. Therefore, this is 1 divided by 1.5. So sine inverse of 1 by 1.5 is sine inverse of 0.66. Correct? So if I find the sine inverse of 0.66, what we will get is 41 degree. Correct? So IC is equal to 41 degree. This IC is nothing but equal to R2. Therefore, IC is equal to R2, which is equal to 41 degree. So we find the value of this angle of refraction R2. Next, we know that the angle of the prism is equal to R1 plus R2. We have this equation from the derivation of this topic, correct? Angle of the prism is equal to R1 plus R2. Therefore, A is equal to R1 plus R2. R1 is written as it is, plus R2 is equal to 41 degree, and also I know the angle of the prism is 60 degree. Therefore, if I write this as some 60 degrees, what I can find is, I can find the value of R1. Therefore, R1 is 60 degree minus of 41 degree. Therefore, R1 is equal to 19 degrees. So we got the value of R1 now. Correct? So by knowing the value of R1 and by knowing the value of this refractive index of the prism, I can find this angle of incidence. How do you find this? By using Snell's law. By using Snell's law for the first phase. Correct? We are finding this for a first phase. The refractive index is equal to sin I divided by sin R1. For the first refraction, n is equal to sin I by sin R1. So that sin I can be written as n into sin of R1. Let us substitute the values now. So sin I is equal to n is 1.5 into sin R1. Sin of R1. R1 is equal to 19 degrees. So sin I equals 1.5 into sin 19 degrees is 0.3255, and therefore sin I will be equal to 0.488, or if I want the angle of incidence, I can do this sin inverse of 0.488, and finally the value of I is found to be 29 degrees, correct? So we got the value of angle of incidence. So that's all. Now let us move on to the next problem. Now the next problem is a small bulb is placed at the bottom of a tank containing water to a depth of 60 centimeter. What is the area of the surface of water through which light from the bulb can emerge out? Refractive index of the water is 1.33. So this problem is based on the total internal reflection. Let's understand this problem now. They are saying that we have a surface of water. At the bottom of this water container, they have placed a bulb which is emitting light in all the direction. Say this is the refracted light which is incident at this point, and after this point the ray will be undergoing a total internal reflection. Only this ray can emerge out along the surface of water like this. Above this point or next to this point, the ray would be undergoing total internal reflection. Therefore, if this is a bulb which is emitting the light in all the direction, which can emit the light only up to this surface. So light can emerge out only from these points on the water surface. Therefore, this light can form a circular patch of light like this. Okay, on the surface of water, it forms a circular patch of light like this. Only up to this, a light can emerge out from this bulb, not above this one, correct? So, if I say this is a light which is emitting the light in the straight direction or in the normal direction, and this ray would go like this. So, only up to this area, a light can emerge from this bulb. Okay. Now what is the area of this surface? That is what we need to find. Say this is the center of the circular patch of light, and say this is the radius of it. Now we need to find this radius. If I find the radius, the area will be equal to pi into r square. So we need to find this r only, correct? Now at this point, the ray would be traveling along the interface, so that if you draw a normal here, this angle is, see, this angle is equal to 90 degrees, correct? Therefore, this angle must be equal to the critical angle IC. So, if this is a critical angle, this is also a critical angle, because if you say these are the two normals, then these two becomes the alternate angles. Fine. Now, by using this, let us find out this radius r, and in turn, we can calculate the area of this circular patch of light. So, first let us find out the value of IC. How do you find this? We have a formula, n is equal to 1 divided by sine of IC, so that sine IC equals 1 over n, or IC is equal to sine inverse of 1 by n. So they have given the refractive index of water. This is a water medium. So for water medium, the refractive index is equal to 1.33. So this is sine inverse of 1 divided by 1.33. And IC equals, if I find this value, what you will get is sine inverse of 0.7519, and if you find the value of IC, you will get 48 degree 45 minutes, correct? So the value of IC is found to be 48 degree 45 minutes. Now this bulb is at a depth of 60 centimeter, they are saying, correct? Let me mark this point as some A and this as some C. We have a right angle triangle now, ABC, correct? ABC is a right angled triangle. Therefore, if I use the property of this right angle triangle, we can find the value of this R. Let us define tan IC for this. Tan IC will be equal to opposite side is AC divided by adjacent side is AB. Therefore, AC by AB, or tan IC equals AC is nothing but radius R divided by AB is nothing but the depth of that bulb, which is given as 60 centimeter. Let us substitute that as 0.60 meter, which is written in meter. Therefore, R is equal to tan IC into 0.60. I know that the value of IC is equal to 48 degree 45 minutes. Therefore, this is 48 degree 45 minutes into 0.60. You multiply this, what you will get is, this will be 1.1404 into 0.60, and finally we obtain the value of R as 0.6842 meter. So we got the value of R, and what we need to find is what is the area of this surface, area of this water surface up to which a light can emerge out. So to find that, area is equal to pi r square. Pi is 3.14 into R is 0.6842 the whole square, and area will be equal to 1.45 meter square. So we got the value of area as 1.45 meter square. Fine, we'll move on to the next problem now. The next problem is, a rectangular block of glass lies at the bottom of a vessel containing water. A ray of light incident on the surface of water at 40 degree passes through the water and falls on the top surface of the glass slab. Calculate the angle of refraction in glass. Given that refractive index of glass is equal to 1.5 and refractive index of water is equal to 1.33. Let's understand the problem. They are saying that we have a water container which is filled with the water, and at the bottom of this water container we have a rectangular glass slab. This is a rectangular glass slab. So here we have three mediums. This is air, this is water, and this one is glass. Okay. Initially, a ray of light is falling on the surface of water with an angle of incidence of I1 equal to 40 degrees. Next, the same ray is going to refract into your water and which falls on the glass surface like this. This is falling on the glass surface. Now here, let us say that this is the angle of refraction R1. This is angle of refraction R1, and this ray is now going to fall on the glass slab. So say this is a normal, and inside the glass slab, the ray is again refracted like this, which bends towards the normal. Say this is the angle of incidence for the second refraction, correct? This becomes I2. I will write this as I2. This I2 is nothing but the angle of refraction for the second surface. Finally, this is the angle of refraction at the glass slab. We need to find what is the value of this R2. Okay, a ray of light is falling with an angle of incidence I1, and it is refracted in a water with an angle of refraction R1. Again, it is falling on the glass slab with an angle of incidence I2, and finally it is refracted with an angle of refraction R2. We need to find this angle R2. By this diagram, the R1 and I2 are same because they are nothing but alternate angles, correct? If this is a normal and this one is a normal, R1 and I2 must be same. Therefore, we can write the condition of R1 is equal to I2. Now, let us solve this problem by considering the two cases. First case is when light travels from air to water. Okay, light is traveling from air to water. This is the first case. So in this case, using the Snell's law, refractive index of water with respect to air, this is equal to sine of I1 by sine R1, correct? This is sine I1 divided by sine R1. So we need to find this R1 now. Let us substitute this. So take the sine R1 towards this. So sin R1 is equal to sin I1 divided by NWA. So sin R1 is equal to sin I1 is sin 40 degrees divided by NWA. NWA is nothing but refractive index of water with respect to air, which is given as 1.33, which is the absolute refractive index. This will be 1.33. Let us find out this. Sin R1 is equal to, the value of sin 40 degree is 0.6428 divided by 1.33, and if you do this, what you will get is 0.4833. Finally, R1 equal to sin inverse of 0.4833, and this R1 will be 28 degree 54 minutes. So we got the value of R1. Next, consider the second case. In the second case, the light is traveling from water to glass. The second case, the light is traveling from water to glass. Therefore, when light travels from, so in this case, if you apply the Snell's law here, the refractive index of glass with respect to water you have to write, correct? So, refractive index of glass with respect to water is equal to sin I2 by sin R2, correct? Sin I2 by sin R2. Let us write this, sin I2 by sin R2. Now, this NGW is written as NG by NW, which is equal to sin I2 by sin R2. So we need to find this R2. So take this R2 towards this. Therefore, you will get sin R2 equals sin I2 into NW whole divided by NG. But we know that I2 is equal to R1. So we have already made this point. R1 is equal to I2. Therefore, the value of this I2 is equal to 28 degree 54 minutes. Correct? So let us substitute the values now. So sin R2 equals sin I2 is sin of 28 degree 54 minutes into NW is 1.33 divided by NG is 1.5. Now sin R2 is equal to 0.4285, or R2 is equal to sin inverse of 0.4285, and finally the angle is equal to 21 degree 22 minutes. So we got the value of angle of refraction at the second surface, correct? We'll move on to the next problem now. The next problem is, a convex lens has a focal length of 0.30 meter in air. Calculate its focal length when it is immersed in water. Given that refractive index of water is equal to 4/3 and refractive index of glass is equal to 3/2. Imagine a convex lens which is in air. Okay, so this is in air. So when this convex lens is in air, its focal length is given as 0.30 meter. Next, what they are doing is they are immersing the convex lens completely into a water. So if it is immersed in water, what happens to the focal length of this convex lens? That is what we need to find. So here let us consider this by two cases. So in the case one, when the lens is in air, the focal length is 0.30 meter. So now by using a lens maker's formula, 1 by f1 is equal to n21 minus of 1 into 1 by r1 minus 1 by r2. So here 2 and 1. The second medium is glass and the first medium is air in the first case, correct? NGA refers to refractive index of glass with respect to air initially. So this is 1 by f1 which is equal to NGA. So refractive index of glass with respect to air, which is given as 3/2 minus of 1 into 1 by r1 minus 1 by r2. Let us write this as it is. Next, 1 by f1 is equal to, if you take the LCM here, so you will get 3 minus 2. So 3 minus 2 by 2, which is equal to 1 by 2 into 1 by r1 minus of 1 by r2. Take this as equation number 1. Next, the second case. In the second case, when the lens is in water. New focal length is equal to f2. So we need to find this f2. Let us use the same formula. 1 by f2 is equal to, now the lens is placed in water, therefore refractive index is nothing but refractive index of glass with respect to water, correct? Refractive index of glass with respect to water. Therefore, while writing the lens maker's formula, 1 by f2 is equal to, here you need to write refractive index of glass with respect to water. Minus of 1 into 1 by r1 minus 1 by r2. Now 1 by f2 equals, this is equal to Ng by Nw, correct? Ng by Nw, absolute refractive index of glass divided by the absolute refractive index of water. This is minus of 1 into 1 by r1 minus 1 by r2. We know the values of Ng and Nw. So Ng is equal to 3 by 2 and Nw is equal to 4 by 3 minus of 1 into 1 by r1 minus 1 by r2. Now 1 by f2 equals, so this 3 goes to numerator, 2 comes to denominator, therefore 3 into 3 is 9, 4 into 2 is 8. Therefore this will be 9 by 8 minus of 1 into 1 by r1 minus 1 by r2. Take this as, so if I take LCM here, what we will get is 1 by f2 equals 9 by 8. So 9 minus 8 by 8, which is equal to 1 by 8 into 1 by r1 minus 1 by r2. So take this as equation number 2. Now I have equation 1 and 2. Let us divide them to obtain the final value of f2. First, let us divide the LHS of the two equations. 1 by f1 divided by 1 by f2. This is equal to, RHS of the first equation is this, 1 by 2 into 1 by r1 minus 1 by r2 whole divided by, the right hand side of the second equation is this, 1 by 8 into 1 by r1 minus 1 by r2. So cancel this 1 by r1 and 1 by cancel these two, 1 by r1 minus 1 by r2 on both the sides gets cancelled. So what remains is f2 goes to numerator, f1 comes to denominator, therefore this is f2 by f1 is equal to, so after cancelling these two, we can write this as f2 by f1, which is equal to, 8 goes to numerator, 2 comes to denominator, this will be 8 by 2, or f2 equals 8 by 2 is 4, 4 into f1, correct? 4 into f1. 4 into f1, I know the value of f1 is 0.30 meter, therefore 4 into 0.3 is 1.2 meter. Therefore, f2 equals 1.2 meter. So we got the value of focal length when it is immersed in water. So f2 equal to 1.2 meter. Fine. Up to this, we have solved very important problems of the chapter ray optics. So that will be the end of this session as well as this chapter. Thank you.